Hi everyone. In this video, we will extend our notions of central limit theorem and discuss sample proportions. Again, recall from our previous sections that if x1, x2, xn represent independent and identical variables with the same probability distribution, then their sum will converge towards a normal law. This normal law's average value will be the sum of the expected values of the xk, and its standard deviation will be the root of the sum of the variances of these xk. All variances of xk and expected values of xk are identical. Now, suppose x represents a qualitative binary variable. Think of it as whether a specific individual has a characteristic or not. Let us consider a scenario where a sample of n individuals is selected with replacement from a population whose proportion with that characteristic of interest is p. The value of x for the kth individual that will be selected is denoted by xk. A priori, there is no way to predict if the individual has the characteristic or not. In fact, each xk is a Bernoulli variable. So xk could either be 0 or 1. The expected value of xk is p, and its standard deviation is the root of p 1 minus p, as described by Bernoulli variables in general. For example, at Marinopolis, 80% of the student population state they would accept to return to the college with the recent stabilization of the COVID-19 pandemic. Let variable x take values 0 and 1, where x equals 1 would represent a student that accepts to return to the college, and 0 represents a student who refuses to return to the college. Suppose that two students are randomly selected with replacement from the Marinopolis student population, and let x1 and x2 represent their position with regards to returning to the college or not. Replacement of the selected individuals will guarantee the independence of the x1 and x2 results. Furthermore, since the students are taken from the same population, that is, from the Marinopolis student population, then x1 and x2 must obey the same probability distribution. More specifically, x1 and x2 would both be Bernoulli variables with 80% chances of a success. Therefore, the expected value for x1 and x2 is 0.8, and the standard deviation for x1 and x2 would be 0.4. Now, if this were repeated to n Marinopolis students selected at random with replacement, then the expected value would be 0.8 and the standard deviation would be 0.4 for all n of these selected individuals. Which brings us to a sample proportion. So the proportion of a sample with a given characteristic is denoted by p hat. It is a random variable whose value depends on the individuals that will ultimately be selected from the population. Note that p, the populational proportion, is not a variable, it's called a parameter. And it is the result, not the result of chance or of random selections, because it is the entire population's proportion who has a given characteristic. By definition, a sample proportion is the sum of the successes and failures each of the x's produce. Now remember, all of these x's are either 0 or 1. So the sum of the ones that we obtain will give us a proportion out of n. I factored out the 1 over n once again to give the impression of a linear transformation. The expected value of p hat can be obtained by taking 1 over n out of the expected value, by distributing the expected value to the sum of the xk's, and then by remembering that because we're dealing with Bernoulli experiments, each expected value is p. Now with the addition of these n p's and the product with 1 over n, the end result will be p. In other words, we would expect that the sample proportion is equal to the population's proportion. With regards to the variance of p hat, once again, properties allow us to withdraw 1 over n as long as we square that term. Variances can be distributed to sums as long as we are assuming that these variables are independent. And because each of the xk's is the result of a Bernoulli experiment, then all variances are obtained from p times 1 minus p. So the addition of these n p 1 minus p over n squared simplifies to p 1 minus p over n. Therefore, the standard deviation for p hat will be the root of p 1 minus p over root of n. The variability of p hat therefore depends on how big the sample is. It also depends on the value of p itself, so the populational proportion. Again, what can we make of all of this? Well, remember that the variables we are using are all identically distributed. They are independent, and considering there's a sufficient number of them being added, then their sum will act like a normally distributed variable. So, since the sample proportion is obtained by adding Bernoulli experiments, then p hat will act like a normal variable centered around p with standard deviation root of p 1 minus p over root of n. So although this is not exactly the central limit theorem, it certainly is an extension of it, where p hat is acting a little bit like the sample average was in our previous section. This time, we can apply this theorem as long as n is at least 30 and np, n1 minus p, are at least 10. Again, on the independent selections, although in theory, samples that are selected without replacement do not fulfill the criteria of independent results, we treat such cases as independent when the sample size is small compared to the population size. Here's an example we had begun earlier. So at Bernoulli, let's assume 80% of the student population state that they would accept to return to the college with the recent stabilization of the COVID-19 pandemic. Suppose a sample size of 64 is selected from the Bernoulli student population. Then, according to our extension to the central limit theorem, p hat should be centered around 0.8 with standard deviation p 1 minus p over root of n. So p hat will be centered around, will be a normal law, pardon me, with 0.8 average and 0.05 standard deviation. Although I haven't checked out these conditions, the n value is definitely above 30, and you can verify that 64 times p and 64 times 1 minus p are both greater than 10. Applying this in a probability situation, the probability that a sample proportion will be under 0.7 in this scenario would be 2.275%. In other words, if 80% of the student population is willing to return to the college, it would be very unlikely to select at random a sample of size 64 where less than 70% of the surveyed students would in fact agree to return. And that concludes our section on sample